In this video, we're going to start looking at surds. I'm going to start the video off by drawing a right angle triangle. If we have a right angle triangle, we can use Pythagoras' theorem to find a missing length. So if I just put the right angle here, and we said that this one was 3 centimeters, this one was 4 centimeters, and we wanted to find the length of the hypotenuse x, we could either spot that this was a Pythagorean triple and write down 5, or we could use Pythagoras' theorem of a squared plus b squared is equal to c squared. So if I do that, we can say that x squared is equal to 3 squared plus 4 squared. So we could write now that x squared is equal to 9 plus 16. We can say that x squared is equal to 25. And x, as it's a length, will be equal to the positive root of 25. And that gives us that x is equal to 5. So we have an integer value, a whole number, and we have a perfect square. That's not always going to be the case. So if we use Pythagoras' theorem on a different triangle, we might not get an integer value and we might not have a perfect square. When that happens, we say that the answer can be left in surd form. So let's go ahead and draw another triangle. So if I do this one, what we're going to do is put on, again, we'll have 3 centimeters here. This time I'm going to put on now one of the other shorter sides. We're going to have 5 and we'll have y. So we can say using Pythagoras that y squared is equal to 3 squared plus 5 squared. We can say that y squared is equal to 9 plus 25. Y squared is equal to 34. Again, y is a length, so we say that y is going to be the positive square root of 34. At this stage, we would leave this in exact form. Exact form means that we don't write this as a decimal. We could go ahead and write that as a decimal, but it will reduce the accuracy of our workings if we were to use this for any other calculation. So we can write now the root of 34. Now if we think the root of 36 is 6, the root of 25 is 5, so this should be probably about 5.8. So if we just look at that, this now is in exact form. We would leave it like so. 5.83 to 2 decimal places. So that now is a surd. It's when we don't have a perfect square like here. So we would write it in what we call exact form. So exact form. So if you see a question in exam and it says leave your answer in exact form, it's telling you not to get a calculator out on that, but simply leave it as the root of 34. A surd is an irrational number. Another example of an irrational number that you might have seen is pi. Pi is approximately equal to 22 over 7. It's not equal to that, and we couldn't express this as a fraction where we have an integer in the numerator and an integer in the denominator. It's now 3.14159 and so on and so forth. When we have an irrational number, they are non-terminating, non-recurring decimals. So this goes on for, well, it just keeps going. I believe a guy has recited about 100,000 digits of pi, and it took him a day to do. But this is never going to end. So if we were asked to leave our answer in exact form, we would just write pi. We wouldn't now go ahead and write 3.14159 because that's not exact. Every time I write this as a decimal, I'm losing accuracy, and I'm also making any calculations I do by hand incredibly hard. So here we go. Here's an example of an irrational number, and it's the root of 34. Okay, in the video, what we're going to do is start off by looking at some very basic examples of surds and how to simplify them. This one is in its simplest form. Some, though, we can manipulate to write in a slightly different way. So let's go ahead and look at some of these. We're asked to simplify the following. The square root of 36 is going to give us 6. So we can simply write now that root 36 is going to give us 6. When we have now the root of a a is going to be a value greater than 0. So this now is a positive number. We could have plus or minus this answer, but the actual value under the root is a positive quantity. Okay, let's look at the root of 8. We're asked to simplify the following. This isn't broken down into its simplest form. We could of course leave it like so, but we would want to write this now in its simplest form. If we look at this, we've got now the root of 8. To simplify this, I look for multiples of square numbers in 8. So if I write now that that is 4 multiplied by 2, using the laws of Surds, I can split this up and write this now as the root of 4 multiplied by the root of 2. This again is going to give us an integer value. The square root of 4 is going to give us 2. So we can write this now as 2 times by the root of 2, and we can now write this as 2 root 2. So this is our simplified answer. If we did it in a calculator, we would have now the root of 8, and the calculator will default to 2 root 2 as it's in its simplest form. So 2 root 2. That's going to be just under 3. If we think the root of 9 is going to give us 3, we've got now 2.82. So again, this will not stop. So if you're dealing with an exact value, don't write 2.828. That's not the exact value. That's just a decimalised, truncated answer as an approximation. We would simply write now the root of 8. The advantage of this is if I said now the root of 8 times by the root of 8, and I'll just do this here. So if we wrote the root of 8 times by the root of 8, what we've got here now is the root, and we could write this now as the root of 8 times by 8, which gives us now the root of 64, which of course gives us 8. Alternatively, what we could use is one of the laws of Surds. As we go through the videos, we will look at more of them, but if we've got now the root of a multiplied by the root of a, this simply gives us a. That makes perfect sense, and we could employ it here. Okay, so let's go ahead and simplify a few more of these. The root of 12. So what I'm doing is trying to spot a square number that's multiplied to give me 12. So just if you're unsure, just go down your square numbers. So the square numbers are going to be 1, 4, 9, then we're going to have 16, we're going to have 25, we're going to have 36, we're going to have, after that one, 49, 64, 81 and 100. So if we look at this one, can we simplify it? Well, I'm thinking to myself that 4 will go into 12 3 times, so we can write this now as the root of 4 multiplied by the root of 3. We can split this up. We can write now that this is the root of 4 multiplied by the root of 3. We've already seen now that root 4 can be written as 2. The root of 3 is in its simplest form. This is about 1.7, the square root of 3. So root 3 as an approximation is about 1.73. But we would write it now as 2 lots of root 3. This step here is not necessary. I'm simply showing how I'm splitting up. So that would be 2 root 3. If we look here, what we've got now, we could say if we have the root of a multiplied by the root of b, this is going to give us the root of a times by b, which of course will give us root ab. So essentially all we've done is gone backwards with this. So if we look at what I've done, I've taken the root of ab, I've written it now as the root of a times by b, and then just split it up, and then just simply converted our perfect square and done that. So if we just match what I've done here, that makes perfect sense. There is an alternative approach if you wish. I'm going to do a couple of examples, but you don't have to do this. I think it's easier to spot the perfect squares. What we could have done here is prime factorise 8. So if we prime factorise 8, it's 2 times 2 times 2. So what we could have written is that this is the root of 2 multiplied by the root of 2 multiplied by the root of 2. Not quite sure why I've got some strange arrows on this. Let's just go ahead and change this over. Now we know that the root of 2 times by the root of 2, using this particular property here, root a times by root a is a, we could simply go ahead now and write that this was going to be now 2 root 2. So that is an alternative approach if you want to simply prime factorise. So if you can't spot squares, these square numbers within the root that are multiple of them, you can do this. It can be a bit taxing. Certainly with this example here it would be, but that is an alternative approach. So this one here, if we prime factorise this one, this is 2 times 2 times 3, so that would be the root of 2 times by the root of 2 times by the root of 3. Once we have these two here, multiplying them, we get 2 root 3. As stated, that is an alternative approach. I personally prefer to spot the square under the root. Okay, let's look at this one. So what we've got then is the root of 27. I think that's 9 times by 3, so we can write instead the root of 9 times by the root of 3, which of course is going to give us now the root of 9 times by the root of 3. That gives us 3, we know that, that's a square number, so this would give us 3 times by root 3, and our final answer would be 3 root 3. As stated, you wouldn't have to show this, you're simply splitting it up. I'm doing it step by step, and we go from there. This one just here, a square number that goes into 50, that sounds like 25. So we'd have now the root of 25 multiplied by 2, which we could write as the root of 25 times by the root of 2. And we know that the square root of 25 is 5. I'm going to skip this step and simply write 5 root 2. Anytime you do a question like this, it certainly won't be a calculator question, but initially if you want to test this out, simply go into your calculator, type root 50. This will default now to 5 root 2. You can of course turn these backwards, so if it said put this back under the root, all you're going to do is square this number and multiply it by the value under it. So for example here, square this number, that gives us 9. 9 times by 3 is 27. Generally speaking, we would undo them, but sometimes if you wanted to put them back in for your own ease of use, you can do that. Okay, the root of 1200. So let's think logically. We're looking for the biggest square number that we can get in here, and I've just said 1200. So to me, that says that I'm going to have 12 multiplied by 100, or 100 times by 12. So this is a slightly harder example, because we're going to have to simplify a couple of times. So we could write this now as the root of 100 times by the root of 12. This is going to give us now 10, square root of 100 is 10, and then we can have 10 root 12. We've already seen that root 12 is not in its simplest form. We did this one on the previous screen, and we saw now that the root of 12 was actually 2 root 3. So what we've got here now is the following. We've got 10 multiplied by 2 root 3. Well, 10 times by 2 is 20, and then we're going to end up now with 20 root 3. Okay, now, could I have done that any easier? Well, if we look at it now, thinking back, what we could have written here, instead of 100 times by 12, is the root of 400 times by 3. So don't penalise yourself if you don't find the greatest square number in there. And if we just look at this, this is the root of 400, multiplied now by the root of 3. That's going to give us 20, and we'd have 20 root 3. So, again, I chose 100. I should have really chosen 400, but it doesn't matter massively. It was the first one I thought of. Again, if you want to check that in your calculator, the root of 1200, that's going to give us now 20 root 3. If you typed in now the root of 12 times by the root of 100, exactly the same. This should now default to give us the 20 root 3. So you can split those up and work forwards and backwards with them. Okay, this one's quite nice. The square root of a squared. All this is saying now is the square root, so this is the square root of a multiplied now by the square root of a, which of course is going to give us now a. We saw that property. Whilst we're here, I'll introduce now some notation. If we're working with surds, a to the power of 1/2 gives us now the root of a. So sometimes when you're doing, for example, calculus with differentiation and integration, you'll be given something along the lines of, let's say we were asked to find now the integral of 2 root x with respect to x. When we're integrating, which we'll come on to later, we could write this now as 2x to the power of 1/2. So we'd integrate that as we use now the indices for our integration. So these things now are interchangeable. This is the half power or the second root, and that gives us now root a. So all I've done is gone ahead and split that up. If you wanted to look at that in the form of an index, you could write that now as a squared to the half. And using the laws of indices, we multiply these two. So 2 times half is 1, a to the 1, which of course is going to give us a. So different approaches. Okay, let's look at the next one. This is the root of 3 cubed, and we need to write it as a surd. All this is saying then is the root of 3 multiplied by the root of 3 multiplied by the root of 3. One way to look at it, that's going to now give us 3, so we'd have now 3 root 3. And that would be our answer. All I've done is taken root 3, times it by root 3, and times it by root 3. Okay, we're going to do one more. This is, I would say this is an extension question as we're dealing now with the rules of indices, and also we've got now a surd value here. So if I just rewrite this now, what we've got then is the square root of 5 to the power of 4. So I'm just going to write this as 36 multiplied now by 5 to the power of 4 square rooted. That's going to give us 5 squared. So one way we could look at that is like so. If you wanted, you could write this out, if you really wanted, as now the following. What we're going to have is 5 times by 5 times by 5 times by 5. So if we thought of splitting that up, it would be the root of 5 times by the root of 5 times by the root of 5 times by the root of 5, which is another approach. That's going to give us 5. That's going to give us 5. And of course, we'd have 5 squared. So lots of different ways of doing that. This, I kind of bolted this on at the end as a sort of bit of extension. Okay, so if we just put a little 1 here, again, we're multiplying now the powers. So this would become 36 to the power of 1/2. And then we'd multiply that now by 5 to the power of 1. If we go ahead now and do 36 to the half, this is the same as the square root of 36 times by 5. That's going to give us 6. 6 times by 5, that's going to give us 30. So if we type this into a calculator, let's see if we can do that. What we're going to have is 36. We're going to have the root of 5 to the 4th, and then we're going to raise all of this now to the half power. So this one was included, so I could put in either a fraction and put in a half, or I could just put 0.5. That should now give us the 30 that we've just found. And as we can see, we can use the laws of indices, rules of indices, and also surds to manipulate that. So a couple of different approaches. If you haven't yet really looked at the rules of indices, that might have been a slightly more challenging one. Okay, so there's a basic introduction. If we just go back and look, what we've got here now is our first triangle. When we've got a perfect square, we can write the value as an integer value. If we don't, we write it in exact form. Exact forms that means that we don't write this now as a truncated or cut off decimal answer. We've seen that pi is 3.14159 and so on and so forth. We would just leave this now as pi. It is what we call an irrational number. This cannot be written as a over b, where a and b are integers, which means it's irrational. In terms of just simplifying surds, we can go ahead and use the properties now that these are multiples of square numbers if we can break them down. So I looked at just finding a square number, ideally the highest. As I saw with this one, I could have chosen 400 over 100, and we simply go through this particular method. You wouldn't necessarily have to show this in any workings. An alternative approach was to prime factorise the number and simply use the property now that the root of a multiplied by the root of a gave us a. In the next few videos, we're going to look at a few more of these rules and then apply them to some more challenging problems.